You are the Science Alliance. This is the second IGCSE lesson on electricity. So next week, we're going to start things like current and voltage and resistance and power. But this week, we're doing a kind of a gentle warm-up to electricity, conductors and insulators. Now, admission, I think I might have told you something last week that was wrong. I may have said a sentence that was incorrect. I want you to guess which one it was. I've written some sentences on my screen, and yeah, I want you to, one of them is wrong and the others are true. Which one do you think was a barefaced lie? Have a look at this. Doesn't matter if you didn't see last week. One of these is not right. What do you reckon? Opposites attract in physics, is that true? Charged objects aren't attracted to neutral objects, is that true? Electrons can be transferred between objects, but can they? Materials can be tested to find out if they're charged. Really? Electrons can move from balloons to hair? What? Atoms have positive charges at their centres, and electrons can flow through humans. One of those is not true. I've given you a clue with some pictures. You've got a picture of some cling film, a picture of a balloon stuck to a wall, and a picture of some little bits of paper stuck to a balloon. Go on, like, I don't know, 5 seconds. 5, 4, 3, 2, 1. It's... I'll tell you actually. Let's do a little activity to get us thinking, and then I'll tell you. Did you bring some sort of cheap plastic packaging? It doesn't have to be a plastic bag actually. It can be anything that you've bought something wrapped in plastic. And if you've got a pair of scissors, can you cut about a sort of 2p sized bit off the plastic bag? Try and do it in a place where you can still reuse the plastic bag. Yeah, we don't want to render plastic bags unusable. But yeah, if you could have about a 2p sized bit of plastic, that would be very helpful. And then you know what you got to do. If you came last week, you know you have to rub it on your head. Rub this tiny little bit of plastic on your head. So what's happening? Okay, refresher from last week. Everything's made of atoms. Atoms are like positive balls called protons with tiny little negative balls whizzing around them, and positive and negative things attract. Okay, so most things are neutral. Most atoms have the same amount of protons and electrons. So stuff is neutral, right? The chair is neutral, these cards are neutral. What's happening here? Can you remember what's happening? Electrons are being rubbed off the bit of plastic bag and onto your hair. Yeah, we did this last week. So the bag has lost negative charge, so is now positive. And our hair has gained electrons, so our hair is now negatively charged. So once you've done that, we did this last week, if you hold the positive bag up to the negative hair, you should find that it's a little bit attractive. Yes. Now stick your bag to something else, like just anything that you can see. Have a look around. What are you going to try and stick this little bit of plastic to? What will it stick to? Can you think of anything that it won't stick to? I'll start with my whiteboard. Will this little bit of plastic stick to my whiteboard? Yes, it will. Will it stick to my face? Discovered this yesterday. Yes, it will stick to my face. Can you think of anything that it would not stick to? Will it stick to this card? It will stick to the card. Will it stick to the basket? Yes, it will. So we did this lesson on Facebook yesterday, and people were saying it's not going to stick to metal. So I have an aluminium can here. You might have brought one too if you're going to do the activity with me. Will it stick to metal? Yes, it will. What did someone else say it wouldn't stick to? Oh, glass. Yes, someone said it wouldn't stick to glass. What do you reckon? It will stick to glass, people. News just in. What's that about? What is that? So, last week, I threw a lot at you. We briefly mentioned, because I just wanted to do the cool experiment activity where you make water move. We talked about how water particles, this is the water particle, apologies chemists. Water particles are a bit positive on one side and a bit negative on the other side, right? It's called a dipole. So we held a positive bag near the water, and the negative side of the water particle got attracted to the positive bag. That is not what's happening here. Not every single thing we've stuck the bag to has been a dipole particle. What's going on? Well, you might have guessed that the answer to this question was it's charged objects aren't attracted to neutral objects. That is not true, as you've just seen, right? Because our faces are neutral. So what is happening? I'm going to give you 10 seconds to try and think about that. How did this plastic bag, knowing what you know about electrons and protons and stuff, how did this little piece of plastic bag stick to literally everything we could find in our houses? There is, as usual, a Facebook post on my page, Facebook page, if you want to go there and jot down your answer. Just have a think about it. Wish I could hear what you're saying. So the bag is positively charged. The bag has lost electrons. So the atoms on the bag have fewer electrons. Shall I tell you? Did you an animation? Here we are. Here's an extreme close-up of some atoms, say, in a wall. So these are carbon atoms. Actually, you can see they've got 6 protons in the centre with 6 electrons whizzing around the outside, okay? Just whizzing around in a sort of fairly random cloud. Along comes a negatively charged balloon. What are those atoms going to do? Be careful here. What is going to happen to those atoms? Well, I cannot say this enough because some of you are still going to get it wrong in your GCSEs. The protons stay where they are. The protons stay exactly where they are. They are the atoms that are making up the wall. Like, you don't hold a balloon up to a wall and have bits of wall like pop off. So the protons, the centre of the atom stays where it is. But the electrons are free to move around, right? Because they're just whizzing around in a cloud. So what they do is they get as far away from those other electrons as they can. Because, as we know, like charges repel. Electrons and electrons move away from each other. So this leaves a slightly more positive side on facing the balloon, yeah? So if all the electrons have moved away from the balloon, then that's a more negative charge on the opposite side and a more positive charge facing the balloon. So because opposites attract, yeah? So the balloon sticks. Again, yeah, you've got to be very careful. It's not that the positive charges have moved, but because the negative charges have moved away, that it's more positive. All right? Is that okay? So my question to you, a little bit of brain exercise. Last week, we didn't stick balloons to walls. It's not good to get people to blow up balloons, is it? But we did a thing where we picked up little bits of paper, say, with a plastic bag. Like, in these scenarios, is the paper charged? So if I use a balloon to pick up some scraps of paper, is the paper charged? That is your question. So I've got a negatively charged balloon here, picking up some bits of paper. Is the paper charged in this scenario? Explain why not? Say out loud or scribble it on a bit of paper, please. What do you reckon? A lot of incorrect answers to this on Facebook, which sort of pleased me. It meant that people were thinking, and, you know, that I was teaching you something and you didn't know it all already. So I'll give you 5. Is the paper charged, and why? If you think it is, or if you think it isn't, what's your reasoning? The answer is no, it's not charged. The reason you wouldn't say that it's charged is because the paper still has the same amount of positive and negative charges. It's still neutral, okay? It's just that the charges have moved around. So these atoms, they've got 6 protons, they've got 6 electrons. That's a neutral charge overall. The electrons might have moved, but they've still got the same amount of electrons as protons, right? So it's still neutral. Okay. Let's do an activity to talk about other ways that things can be attracted to each other, right? So if you've got an aluminium drinks can, you can do this activity. If you haven't, well done. That probably means you have good drinking habits. I only have this one can that my husband drank some beer out of, and it label made it all sticky, so I had to rub flour on it. So it's gross, but it'll work. You can watch this one. So if you're doing this experiment, this activity, you need to get a big bit of plastic and really rub it on your head. Because it's been a little bit hit and miss. Sometimes it's worked really well, and sometimes it hasn't. So I want to make sure it works for you. Right, so again, just really charging the bag. Electrons being pulled off the bag and onto my hair. So the bag is positively charged. What are you saying about the can? Positively charged, negatively charged, or neutral, this can, at the moment? Neutral, innit? We would assume. Right, let's try and flip the screen without decharging the bag. There we go. You ready for this? You ready? Someone start humming Harry Potter music if you're familiar with Harry Potter. Gasp! Look at that! Look! Can you see that very clearly the plastic bag is not touching the can, and yet the can is rolling around? Wow, that's amazing. Okay, that's the best it's been. Thanks, YouTube, for sharing this moment with me. How good is that? What is happening? Why on earth is that happening? Oh, this is great. I could do this all day, but we have to learn stuff. Why is that happening? Why that's happening is not to do with dipoles, and it's not really to do with electrons. I'll tell you why. We have to talk about what is going on inside metals, because you might have heard me use this word conductors before. So metal is a conductor. What does that actually mean? It allows electrons to flow through it. Here, I'll show you. Right. So if you could look deep inside that aluminium can, what you would see is, I'll just draw one proton, okay? It's obviously more than one proton, but you would see the positively charged protons staying where they are in the aluminium can, right? The atoms aren't moving around everywhere. But the electrons in metals, they're free. That's actually what physicists call them, like that's the word. They're free electrons in metals. They can just move around wherever they like. They're not bonded to any one particular proton. They can jump from nucleus to nucleus, like group of protons to group of protons. And that is what electric current is, actually. It's just, well, it's any charged particle flowing, but in metals it will always be electrons flowing. So the reason why you've got copper wires inside all your electricity in your house is because copper is obviously a metal, so it's got this same structure. So if you put a negative charge, like a battery, next to some metal, then the electrons, which are free to move, will flow away from the negative thing, right? Be repelled by the negative thing. So they're moving. So next week we'll talk a lot more about current. That's basically what current is. It's just charged particles flowing. And this is why metals are excellent conductors. They're very good at having charge flow through them because all their electrons are free. There are some other sort of surprising things. If you came to last week's periodic table lesson with me for all ages, then you'll know a bit about graphite. Graphite is actually just carbon atoms arranged in a certain way. Graphite is actually the material that's inside your pencil. It's not lead anymore. Turned out lead was toxic. But yeah, graphite is carbon particles bonded together in such a way that electrons are free to flow through them. Water is generally a good conductor because it tends to have lots of impurities in it, which also flow. You are an excellent conductor. We'll talk about electric shocks in future lessons because you've got lots of particles in you that can flow. So yeah, what this structure is called is a lattice arrangement. If you've heard the word lattice before, if you're anything like me, it was just in relation to pi. So this is like a lattice on top of a pie, right? This is what's going on inside a conductor. You see the similarity? So the electrons, anyway, inside the conductor, they are free to move. So kind of the opposite of a conductor is an insulator. Like this plastic bag is an insulator. Does not allow charge to flow through it, right? That's why electric cables are wrapped in like plastic or rubber, because you don't get an electric shock because the electricity can't flow through the rubber. So in insulators, the electrons are bound to their atoms, just like we saw with this wall thing that I showed you, right? Inside insulators, electrons are still bonded to their protons. They can move around, like to different sides, but they can't just pop off and run away. They're not free in the same way. So, for your exam, you need to be able to think of a simple experiment to show whether something is a conductor or an insulator. It's not rocket science, this bit. What do you reckon? If you were looking carefully when I was doing the aluminium can activity, you might have already spotted what I'm about to do. Can you think of an easy way of working out whether a material allows electricity to flow through it or not? Well, what you do is you build a circuit. This is just a very simple one. You just get a battery and some wires and a light bulb and some wires. So if electricity has to flow all the way around the circuit to make the bulb light up, okay? So you just take a little bit of wire out of the circuit, put some different materials in, and if the bulb lights up, then obviously electricity is flowing. So the thing you've stuck in the circuit is a conductor. I'll show you, because I got this excellent electronics kit from the chow shop. So I've got batteries, light bulb. These blue things look a bit weird, but they're just wires. There's wires inside there. I'll show you. Look. So I've just left a gap in the wire, and I'm going to put something across it, and we'll see if the bulb lights up, okay? First up, this wooden honey stirrer. Thanks, Mum. It's one of my Christmas presents. What do you think? Is this wooden honey stirrer going to make the bulb light up or not? Ready? Okay, the bulb is not lighting up. Right. Now be very careful here because I am trying to trick you. I'm trying to trick you. What can we conclude about this wooden honey stirrer based on what you've just seen? Based on exactly what I've just showed you, can you draw any conclusions about the wooden honey stirrer? And if so, what can you conclude? So I know that some of you are saying it doesn't conduct electricity. It's an insulator. It doesn't allow current electrons to flow through it. Well, maybe. Let's try it with the spoon. What do you reckon? Is this spoon going to conduct electricity? Is it going to allow electrons to flow through it and light up the bulb? Let's see. You ready? No. Is that a surprise? Because I just told you that all metals conduct electricity. All metals are good conductors. Even mercury, the deadly toxic cool one that stays liquid at room temperature, they all allow charge to flow through them. So what's going on? Why? Well, what am I? Can you see what I'm doing here? Well, can you draw any conclusions about the metal spit? No. Do you see? Some of you at this point will be saying things like, "Oh, maybe the battery's flat. Maybe the bulb is broken." Yes, well done. This is genuine. It could come up. I've seen a past paper question on this. We didn't check that the bulb was lit, did we? We didn't check that the circuit was working before we started sticking things in. So obviously we can draw no conclusions because the whole thing might just be broken. And in fact, I just tricked you by not screwing the bulb in properly. So the bottom of the bulb is metal. It's obviously got to be touching the circuit in order to light up. So let's try that again. Is the spoon going to light up the bulb? Yay! Whew! Good. And the wooden honey stirrer? No, still no, because wood is, as you would probably expect, a good insulator. Plastic fork? We've already talked about how plastic is an insulator. There's no charge flowing through that plastic fork. Good, good. Paper? What do you reckon? 3 seconds. Tell me yes or no. Let's have a go. No, paper is not a conductor of electricity. Scissors, what do you think if it's half and half? If you've got half a handle that is rubber and half a blade that is metal? No, because the electricity can't flow through the electrons can't flow through the handle. But if we open it up, don't try this at home, then we can get the bulb lit up. There we go. Right. So hopefully that's fairly straightforward. Yeah, the big ones to remember are metals and graphite, and generally speaking liquids are good conductors. What they'll probably do is give you a past paper question like this. Have a go at these two. Just some sort of multiple choice thing like this. So, which list contains only conductors? Have a go at this then. Which list contains only conductors? Is it A, gold, copper and paper? B, wood, paper and graphite? C, gold, graphite and aluminium? Or D, plastic, paper and iron? And which list contains only insulators? Is it A, gold, plastic, paper? B, plastic, paper, graphite? C, gold, graphite, aluminium? Or D, plastic, paper, air? Which one? 5 seconds. So the first one, the the conductors were gold, graphite and aluminium. So you would have to know that gold, copper, aluminium, iron, they're all metals, yeah? And the list which had only insulators in it was the plastic and the paper and the air. Well done, if you got that right. So, last thing we need to do is look at some uses and some dangers of electrostatic forces, or like static electricity, okay? If you're doing the EDEXCEL exam, so the EDEXCEL or Cambridge that could be writing your physics IGCSE exam, and they both want you to learn slightly different things, EDEXCEL is very big on you learning about how photocopiers and inkjet printers work. I'm just not going to go through that because it's not covered in Cambridge, and it's quite a lot of detail, and to be honest, I think at this level it is kind of just a memory game. But there's an excellent website, this one, called cyberphysics.co.uk, where they've got all the uses of static electricity that you might need to know. So you can go to that after this, or when this video is finished processing, I'll stick down below in the description some links that you might need. So yeah, you need to know how a photocopier works if you're doing that exam. I mean, it's interesting, but it's just kind of a list of points. And an inkjet printer, but the one that I want to go to is the, in fact, yeah, I might have just given you a spoiler there. Let's see. I want to talk about electrostatic precipitators. I want to see if you can build one, in fact. So, the problem. Human beings love to burn coal, don't we? We've been doing it for years. We like to build it, coal, big factories that run on coal in the old days, and we use it to generate electricity. When you burn coal, a lot of dust is produced and little particles of ash, which would get into the lungs of people who live near the factory, terrible for the environment, and cause a lot of diseases in all kinds of living things. How are you going to stop this dust and ash from getting into the environment? Here we go. Have a go. I think you can solve this problem yourselves. The problem: coal burned to produce electricity releases tiny pieces of ash and dust that cause diseases and damage the environment. Here's the coal. Here's the little particles. You've got a negatively charged grid, positively charged metal plates, 2 hammers that automatically hammer every few minutes, and a funnel, big as you like. There's something rude about the funnel, but I haven't put my finger on it. Can you solve the problem? Go on. See, where are you going to stick the negatively charged grid, the positively charged metal plates, the hammers and a funnel, so that these particles of ash and dust don't fly off into the environment and do lots of damage? You might want to scribble a diagram. Ten seconds. 8. Go on, get scribbling. 3, 2. If you're bored, you finish. You can always like and subscribe, can't you? 2, 1. Well done if you got something. You may well have built an electrostatic precipitator. Let's see how they work. So, what you do is, you get your negatively charged grid and you stick it where the particles are coming off the fire. And this gives electrons to the little particles, right? So all the little particles become negatively charged. And then you put your positively charged plates in their way. And of course, now they're negative, they're attracted to the positively charged plates. So they get stuck on there. And then you just get a hammer. It's not very technical, is it? You just whack it every few minutes, and if you've got a big funnel or hopper or something underneath the plates, then all the little dust particles and ash particles fall into the hopper, and you've caught them. How good is that? Not only have you caught them, they're actually incredibly useful. They can be used to make, I think it's concrete. They've got all kinds of fantastic uses. And they're not causing diseases. Now, textbooks do have a habit of making everything seem extremely clean and straightforward, so I thought I'll show you one for real life. They look like this. Look, I mean, brilliant. So you've got negatively charged rods going into, I've called them positively charged holes, like all these kind of hexagon plates. These are all positively charged, so they collect the dust. Here's another one, another little image. It's great, isn't it? What a simple solution to a really horrible problem. Now we get onto the, it's not fun, is it? It's horrible and serious, but, you know, it's quite interesting. Petrol becomes negatively charged as it brushes against the tubes, putting it into the car. This is a true fact. Yeah, so petrol, this is a huge problem for planes refueling as well, is that petrol acts in the same way as our plastic bag does. I'm trying to draw, wow, it's not, okay, never mind. Yeah, as petrol flows through a tube, then, I can't believe how hard I should have done this in advance, I'm so sorry, I can't draw at the best of times. Yeah, as petrol goes through a tube, then it pulls electrons off the sides of the, because obviously there's a lot of friction there, right? It's travelling quite fast, the tube's quite narrow, so electrons get pulled off the sides of the tube and into the petrol becomes negatively charged. So it also goes into the tank with a negative charge on it. Now cars are grounded in all kinds of ways actually, but we'll talk about what being earthed means in future lessons, but cars are built so that electrons can kind of flow through them and also into the ground as well. So this isn't usually a problem, but, excuse me, obviously I've said that air is a good insulator, but if something that's positive or something that's neutral gets too close to something that's negatively charged, electrons will jump off it and into the neutral thing. I mean, that's what lightning is, right? Just like loads of electrons in the sky making their way down to Earth to try and kind of get away from each other. So this is why, I'm not a car driver, I haven't heard this advice, but when you're filling up your car with petrol, you shouldn't, while it's filling, go back into the car, like to get a jumper or to get your card or something. Because if you're like rubbing against maybe the lining of your car, and say you've got a woolly jumper on, that could quite easily become positively charged. And then while you're filling up your petrol, if your positively charged body gets near the negatively charged fuel, well, in the air, you know that horrible smell you get in petrol stations? Oh, some of you might like it, I don't know. But anyway, that's tiny particles of incredibly flammable petrol. So you get electrons jumping through the air. That's a spark. And that could easily set all this whole thing on fire, right? Terrifying. I read an interesting article about some cars that had to be recalled in Germany because there was something wrong with the car. There was a little bit of metal near where the petrol goes in that wasn't connected to the rest of the car. So as the petrol came past it, that little bit of metal got negatively charged. And because it wasn't attached to any other bit of the car, it couldn't sort of discharge. The electrons didn't have anywhere to go. So there was a spate of fires at petrol stations that a physicist has to investigate, and he discovered that the problem was the electrons were jumping into the people, and yeah, that spark was lighting stuff on fire, right? It's also why you shouldn't smoke in petrol stations, because of the fire. Mobile phones, it's not, there's a myth that people think that mobile phones sort of generate waves. We'll look at waves in future lessons that cause fires. That's not it. It's just that you don't want to be distracted while you're doing this. But yeah, so you might well get asked about the dangers of static electricity, and if you're lucky, you'll get this cool like aeroplanes refueling or cars refueling question. Yeah, I think, and again, I'm just going to put you a link to some other good websites that sort of describe this in detail and give you the bits that closer to the exam you might want to just memorise, frankly. But I've already put some past paper questions in my Facebook group, so if you want to have a look at those, there's a couple of uses of questions there. Right, that is the end of the lesson, apart from my little summary questions to see how much you've understood this lesson. If you have enjoyed this lesson, you know how to support me. I have to say it every time, or this would not be my job. If you go to my YouTube About section somewhere and click the link to Coffee, this is a website called Coffee, where people can support me with £5 or £6 a month. So my ethos is, I just want everything I do to be free, and then if you're in a position to pay me, if you usually pay for your lessons, then you can if you want to. So yeah, there's homework and like further reading ideas on my Facebook group. You might have got the worksheet for this lesson in my Facebook group. All the lessons that I've ever done are available on Catch Up on YouTube for IGCSE. So yes, thank you very much to everyone who's supporting me. I'll send you nice things if you do support me to say thank you, because it is the best job ever. I'll send you rainbow glasses that make you see rainbow. I'm going to show you how they work. I never do. Well, I won't show you how they work, but I'll show you what you see if you put these rainbow glasses on. How good is that? When we cover waves, I think in IGCSE, I'll be advertising them harder because they would actually be quite useful. Yeah, I'll send you a description of how they work, and I'll send you Theatre of Science magazine as well, because it's very good and I want you to have it. Right, I'll do the questions then, and then I'll go and see if anyone said hello on Facebook. Here we are. Which of these is charged? Is it a wall that has a balloon attached to it? Is it a copper wire? Or is it an electron? Which one of those is charged? 3, 2, 1. It's the electron. So as we've discussed, the wall that the balloon is stuck to isn't charged. Its electrons have moved around, but it's still got a neutral charge. And a copper wire isn't charged either. Electrons are flowing through it, but it's still probably got about the same amount of electrons and protons in it. Next question. The electrons in metals are they bonded or free or loose? Which one is it? The electrons in metals are bonded or free or loose? The answer is they're free. I mean, they kind of are loose as well, but the technical term is free. Which list contains only insulators? Is it A, mercury, wood and plastic, B, graphite, air, paper, C, paper, air, plastic, or D, wood, gold, air? Which one of those lists only has insulators in it? 3, 2, 1. It's the paper and the air and the plastic. So electrons can occasionally jump through air, but it's a pretty good insulator. And finally, name one use for electrostatic charge. Name one use for electrostatic charge. Is it a precipitator in a power station, electric current in a wire, or petrol station fires? Which one of those is a use for electrostatic charge? 3, 2, 1. It's a precipitator in a power station. It's fun to say. I was trying to catch you out there because current running through a wire is obviously incredibly useful, but it's not electrostatic charge. So we looked at last week how static means like staying still, stuck on. A current in a wire is doing the opposite of that. It's moving. So a use for an electrostatic charge. A danger of electrostatic charge is petrol station fires, but that's not very useful. So yeah, it's the electrostatic precipitator and photocopiers, which you can learn about in your own time. Okay, you lot, thank you so much for coming. It really makes a difference seeing the little number telling me that fellow humans are tuning into my lesson, and I appreciate the likes as well. I still haven't really worked out why it's useful for me to have subscribers and likes on YouTube, but it certainly makes me feel good. Okay, I'm just going over to my YouTube, to my Facebook page, because I've said that if you would like to leave me some comments on my Facebook post, then I will answer them. If you have not left me any Facebook comments, well, you might want to stick around, because someone might have asked a really good question, or told me a terrible mistake I just made. That's always handy. It's always good to get to the comments at the end of the lesson and find out what mistakes you made. Let's see. Wow, loads of comments, brilliant. Oh, I thought you might have some good answers. Excuse me. Oh, it's Olivia. Oh, yes, come on. Olivia was answering the question about the circuit. So a wooden stirrer is an insulator as long as your circuit is working. Yes, on point answer. Oh, Olivia went to see Charlie in the Chocolate Factory at the Leeds Playhouse. That's so jealous, so jealous. Oh, Olivia P telling me that if you click the like button, it makes fireworks. Okay. Well done, Olivia. That is some excellent. And all the answers are from Olivia's, but different Olivia's. It's making it look like I've only got one friend. I haven't. I've got 2 friends. Oh no, look, there's Chloe. Awesome. Olivia saying, are neutrons important? That's a really good question. Neutrons are really important. They're not relevant to static electricity though. We will talk about them when we talk about things that are radioactive and like hadron colliders and stuff like that, but we're not talking about them yet. Wouldn't the electrons be constantly moving from each other? Yeah, they do. Wood will not make it light up. Well done. Hello, Grace. Oh, loads of brilliant comments. Yes, electrons can flow through. Oh, hello, Helen. Lots of problems getting plastic rubbed on our hair to stick. Wonder why? Oh, okay, yeah. So if you were having trouble getting the plastic to stick after you'd rubbed it on your hair, it might be that you've got hair products, because water is a good conductor, right? So if your hair is slightly damp, say if you've just washed it, or if it's got anything wet on it, then the electrons would be flowing through that and away and wouldn't be getting trapped on the plastic bag. It could be that. It could be that it's a very humid day. If you've got a lot of water particles in the air around you, then they would also conduct electrons off the plastic bag, so it wouldn't be as sticky. Yeah, that might be it. Or it might be the material, like maybe if it's just kind of not the right kind of plastic, it's not as willing to lose electrons as another bit of plastic is. Good question though. There was another good question here that made me think about something complicated. Oh yeah! So Olivia's saying, can you tell us again how friction generates charges? Olivia, all the IGCSE write-ups say static caused by friction. So friction is just stuff rubbing against each other. So the idea is that when you rub a plastic bag on your head, you are rubbing electrons off the bag in the same way that if you rubbed, I don't know, buttered toast on your head, the butter would rub off onto your hair. I have read some quite reliable, like usually very good science sort of websites and blogs and stuff that say it's actually not friction, it's not the rubbing that causes the buildup of static. It's just making them touch. But when you rub, it's like, you know, if you when you rub anything, you sort of get more of it on yourself, don't you? Because like your fingers are getting into all the little cracks. I'm trying to explain it in a simple way and I'm making it more complicated. It might just be that the rubbing increases the surface area. So basically the more hair and bag that can make contact, the more electrons come over. And it might not be friction at all. But I'm not allowed to tell you that because it might not be true, I suppose. And certainly as far as your IGCSE is concerned, friction causes static electricity. So we'll just go with that. But it might not be true. Right, I better go because I'm doing my second periodic table lesson on Facebook in 18 minutes. And I need to try and improve some of the slides because feedback yesterday was it was quite hard. So right, I better go. Thank you so much for coming. I will see you all very soon. Thank you for supporting me. Thank you for liking and subscribing and all that stuff. I'll see you next week. Bye.